What am I missing here? No, Rachel? All right, so click and close to have a look up here. I've got a handout for you. Thought I did. Okay, for some reason that handout didn't get delivered, so I'll get it to you tomorrow. It's in, you know where to find it though, right? It's in the, if you go to Google Classroom, student note templates, this will be the one for 1.6. Okay, last section we're doing. If you decide you want to, it's not so hugely essential. I think you'll be fine without it. So what we're looking at today are solving absolute value inequalities. We've already dealt with how to solve absolute value equations. That was section 1.4. Now we're going to talk about how we deal with absolute value inequalities. We reviewed inequality stuff in 1.5. Let's take a quick look at just a very 10-second review of how we think about solving absolute value equations. So if we have, we want to solve the absolute value equation, the absolute value of u is equal to some number, right? Remember what we did. We used our graphing trick and we're looking for the intersections of the function absolute value of u and the function y equals a, right? And we found that those were the 2 points right here with x coordinates a and negative a. Those were the points of intersection, right? And so we built this pattern. Once we're able to isolate an absolute value and it's equal to a number, we know that we can trade that for the 2 cases. Whatever's inside the absolute value is equal to the positive value of the number, or it's equal to the negative value of the number. And that's how we get our solutions, right? Okay, we're going to do something similar with inequalities. Same picture, only now instead of graphing the 2 functions y equals absolute value of u and y equals a, we're graphing the inequality here. Y is less than or equal to a. Okay? If I graph that inequality, think what that means. That means the boundary line, remember this stuff, right? The boundary line is the line y equals a, and we're graphing all the y values that are either equal to that at the boundary line or less than that. If I talk about a y value that's lesser, doesn't that mean below, right? Because in the y direction, that's the positive y direction, that's the negative y direction, right? So a y value of 4, for example, is less than a y value of 6 because 4 is below 6, right? Give me thumbs on that, okay? So then this whole region that we have graphed here is the graph of the half plane corresponding to y is less than or equal to a. So now we're looking for the intersection of this shaded half plane and the v-shaped absolute value function. So where do they intersect? They intersect in here, don't they? In this whole region in here is the intersection. The intersection goes from there up to there, doesn't it? Right? So the boundaries of the intersection are the points at a and negative a, but this time we're also including all of the points in between. Those are also parts of the intersection where the V-shaped graph is within that shaded half plane. Okay, make sense? So our pattern's a little different then, right? So what kind of a compound inequality does that look like? if it's a single interval bounded on both ends? Is that and or or? What do you think? Give me thumbs up for and, thumbs down for or. Okay, good. I'm seeing lots of thumbs up. That's and, isn't it? Right? So then we have this new pattern we can follow. If an isolated absolute value is less than or equal to, the only difference is, are we including the endpoint or not, right? If it's, in this case, if it's less than or equal to some number, then we can trade that for the two cases that form a single compound inequality, right? Whatever's inside the absolute value bars now is going to be in the middle of an and inequality, and it's going to be greater than or equal to the negative number and less than or equal to the positive number. Okay, give me thumbs. Right, so there's our pattern we're going to use. Now let's put this into practice. Let's solve an absolute value inequality that uses this pattern. So what about that? I've got 2 times an absolute value of some stuff, 3x plus 9. Okay, but we don't need access to that yet, do we? What's the first thing I'm going to do in this process of solving that absolute value inequality? Add 1 and divide by 2. And what's the purpose of that? What am I trying to accomplish? Good. So step 1 is isolate the absolute value, right? Okay, so let's do that. If we add 1 to both sides, we get 2 times our absolute value is less than 6. If I divide each side through by 2, we get our isolated absolute value is less than 3. Okay? And let me do this. I'm going to color code that. What are my colors? Okay. And what's inside now, we can take a peek at what's inside. What's inside is a 3x plus 9. So we isolated the absolute value. What's our next step? What's the next step in the process? What would we have done if it were an equation? We isolate the absolute value, then what did we do? What would we do? Okay, so in that case, we would have set up the 2 cases, right? Where we would have set the argument of the absolute value, what's inside, equal to the positive, or set it equal to the negative. I get 2 equations, right? What do I do now, though? Do you remember that pattern we just talked about? Just in case you don't, there it is. Right? There's the pattern. So what am I doing? Because this ends up being step 2, doesn't it? We're going to set up the 2 cases, which follows this pattern. So how do I write that? I'm going to take my single absolute value inequality, and I'm going to trade it for the compound regular inequality so I can continue doing algebra on it. I can't do any algebra now because this is stuck inside the absolute value. So what goes where? Be brave. What do I do with the 3x plus 9? That's like my u, right? So I'm going to write a compound and inequality. And whatever is inside the absolute values is going to go inside my compound and inequality. So what are going to be the boundaries that surround that then? The endpoints. Okay, good. So I get -3 and 3. Okay, now it's important that you see here that this is the pattern we associate with this kind of an absolute value inequality, where the isolated absolute value is less than a number. If the isolated absolute value is greater than a number, it's going to be a different pattern that we'll see in a second. Okay, but this is the one for a less than. Okay, and now we practice solving this. What are the last two steps to solve for x there? Subtract 9, divide by 3. Good. Okay, so if we subtract 9, then that's going to give us what? -3 minus 9 is -12. In the middle, I get a 3x. And 3 minus 9 is -6. Divide by 3, you told me? That's correct. And I got it. So I'm going to get a -4 over there. I'm going to get a -2 there. And I get my x in the middle. And that's my solution. Okay, give me 1 to 5. Okay. So again, steps. Isolate the absolute value. Create my two cases using a pattern. And then step 3, solve it. Okay, let's try another one. Okay, actually we'll go to the other pattern. So now what if we want to do the other kind of absolute value inequality? What if we have an isolated absolute value that's greater than a number instead? Okay. So if we look at the graphs, then we've still got our red absolute value function. So there's the function y equals absolute value of u. But now in this case, we want to graph the half plane y is greater than a. Well, if this is the value a, right, here's my boundary line, y equals a. Remember this from Algebra 1, right? If I'm not including an equals, then the boundary line is dashed because it's not included. It's only a boundary line, right? And we want to graph the half plane, all the y values greater than, meaning above the boundary line. So here's my shaded half plane. The half plane intersects with my infinite v out here and out there, right? So there's the intersection, okay? If I take that intersection and I just project it down onto the x-axis, just like we did here, when I projected this intersection onto the x-axis, we got this yellow portion of the x-axis, right? Same thing here. If I project it onto the x-axis now, I get this infinite interval here and this infinite interval there. Does that look like an and or an or? That's an or, isn't it, right? So now we're getting an or compound inequality. So our pattern is, if an isolated absolute value is greater than a number, then whatever's inside is either going to be less than the negative number or it's going to be greater than the positive. So it's either going to be extreme negative values or extreme positive values, but none of the medium values in between. Okay? So what am I going to do here then? I've got an absolute value function. There's what's inside, right? I'll just remove that for now. What's our first step going to be? Add 6 because we're isolating the absolute value. Okay. Okay, and so we end up with the isolated absolute value is greater than 18 plus 6 is 24, right? And what's inside is negative 3x plus 21. So what's my pattern then? What do you think? What's my pattern here? Somebody be brave. Tell me what to write. Tell me half of it at least. What's one of the inequalities that's going to be in my OR inequality? Go ahead. Say it again. Negative 3x plus 21. Yeah, you're right. Okay, so whatever's inside. Good. So there's one of them. So one of them is whatever's inside. Negative 3x plus 21 is greater than the positive number. Good. Or how about the other one? Somebody else help us out. What's the other one? Be brave. What do you think? Go ahead. You got an idea? Oh, 24. Yep, you're right. That's 24. Thank you. What's the other half of that OR inequality? Do you remember? What's that pattern? It's greater than 24 or oh, okay, so you're talking about how to solve this? Is that what you're looking at? Ah, okay, good. Right, so we're following, I got you. So we're following this pattern, aren't we? So we did that half of it, right? Whatever's inside, our u, which in this case is negative 3x plus 21, is greater than our number, which is 24. The other part of this is what's inside, which is my, again, that's just my negative 3x plus 21 is less than the negative of the opposite of the number, right? The negative number. So negative 24. Okay, so step 2, we created our patterns. Now we just solve, right? We solve each of those inequalities separately. No big deal. So what are the steps to solve both of them, really? What's the step to solve this one? Subtract 21. Okay, now what? Divide by negative 3. What did I hear? Flip the inequality. Very good. We've got this negative there, right? So we've got to flip this guy around. So that's now going to become a less than. And I just end up with x is less than negative 1. So there's part of it. How about on the other side? Same steps, right? Subtract 21, divide by negative 3. If I do that, what am I going to get? I'm going to get my x by itself. I'm going to have to flip this guy around because I divided by a negative, right? Everybody see that? I got a negative there. So that's going to get flipped, and I'm going to end up with negative. Tell you what, I'm going to show the steps. This is probably a bad place to skip steps. So was that negative 45? Divide each side through by negative 3. Which means I've got to flip that guy around. So I end up getting x is greater than 15. So there's my solution. X is less than negative 1 or x is greater than 15. Okay? Give me thumbs. Okay? All right? So on your notes here, we'll just go through this really quickly. So if I want to look at the solution then of something like this, if the absolute value of x is greater than or equal to 7, think what that means in terms of distances, right? The absolute value of x is the distance from the origin, right? If I want the distance from the origin to be greater than or equal to 7, doesn't that mean something like that? So there's another way to think about why we're getting an OR inequality if we have an isolated absolute value greater than a number, because the distances from the origin have to be big. They're greater than or equal to some number. Interval notation, what would that look like? Negative infinity to negative 7, and I'm including the negative 7, or, so I got my union operator, x is greater than 7. Okay? What about over here? Absolute value of x is less than or equal to 4. So now the distance from the origin is no more than 4. It's 4 or less. So doesn't that just mean that interval right there, right? So interval notation looks like that. Okay? Make sense? So steps to solve: isolate the absolute value, create our two cases, right? Which just means we're going to use one of those two patterns, one of those two inequality patterns, and versus or. Solve both inequalities, and then if you want to write your answer in interval notation, one way to do that is just to graph it first and use the graph to create the interval notation. But maybe you can even skip the graph. You guys could probably skip the graph, I bet. Okay, let's look at just a couple more quick examples. Okay, so this is already isolated, but think about this for a second. Which pattern am I going to use here, and or? And thumbs up is and, thumbs down is or. Already isolated the absolute value. That part's done. But I want to see a vote here. You can be real subtle, but I want to see a vote. I want to see how we're doing. Thumbs up or thumbs down? What do you think? And or? Okay. Okay, I'm seeing a little bit of both, but mostly ands. Okay. It is an and. How come? I mean, I guess you can just remember that. But it might be helpful to think about it in terms of a distance, right? The distance from the origin, if it's less than or equal to 27, that's going to be this kind of an interval, isn't it? That means we're including values that are going to be within those boundaries. Okay? Does that make sense? So that's kind of mentally, that's a way to make that connection. I'm looking at distance, small distances that are closer than 27. That's and. Okay? So here's our pattern, right, that goes with that. Okay? Now from there, we're just solving a compound inequality. We've already had a lot of practice with that. What are the steps to solve that compound inequality? What am I going to do first? Subtract 7. Okay, good. Done. Now what? Divide by negative 4. What do I have to do? Flip the inequalities. So if I do that, if I divide by negative 4, negative over negative is positive. 34 over 4 reduces to 17 halves. 20 divided by negative 4 is negative 5. I flip the signs. Okay, that's my answer, but that looks goofy. What do I need to do with that? What's wrong about that? We talked about this the other day, yesterday. We got to go smallest to biggest. We got to take the whole thing and twist it around, don't we? So it looks like that. Okay. Give me 1 to 5 on that. Okay, you probably just need some practice. I want to get you going. How about this one? First step, got to isolate. So what are the steps to isolate? Add 1. Good, I like it. Divide by negative 4, which means flip the inequality. Okay. So this is and or. Thumbs up for and, thumbs down for or. Okay, this is good. This is thumbs down, isn't it? This is or. How come? because now we're looking for distances from the origin that are bigger than 5. So we're going to be further along the number line. We're going to be outside of -5 and +5, right? So large distances means an OR inequality. There's our pattern. So we create the 2 OR cases, and both of those are easy, right? I'm just subtracting 9, and we're done. Okay? All right. Got a little challenge for you, and then you can work. This will be, you have until Monday to figure this out. Okay, so there's no tricks to this. This is a good little puzzle, though. Let's see. Okay, so I guess I'm gonna have to scroll down a little bit. So here we go. We'll read through it here with you. It's a dark, moonless night in France, 1943. Just good logic puzzle. Deep within German-held territory, out of the inky shadows comes Claudette, the beautiful French resistance fighter, followed by 3 downed Allied crew members who she must get back into friendly hands. They must cross a bridge. They know the Germans are not far behind. It's an old, treacherous bridge, and they have only 1 flashlight among them to see. The bridge can support only 2 of them at a time. 3 on the bridge, and it's curtains. The bridge would collapse. You can only support 2 at a time. Pairs crossing the bridge can do so only as quickly as the slower member of the pair, because they need the flashlight to see. Okay? Each time a pair crosses, someone has to return with the flashlight until they're all safely across. So they're going to shuttle across this old bridge. Okay? Unfortunately, the 3 downed airmen are injured. Here are the times each person takes to cross the bridge. Claudette can do it in a minute. Major Johnson has a twisted ankle and takes 2 minutes. Captain Kangaroo got shot up pretty badly. He has to hop on 1 foot, and it takes him 5 minutes. And Colonel Mustard is in worse shape. It takes him 10 minutes to cross the bridge. Okay? Claudette has rigged the bridge with explosives so that their pursuers can't follow. She's about to set the timer before they start crossing the bridge. What's the shortest time she can set and get everyone safely across the bridge before it blows up? Okay? Think you understand the puzzle? All right, that's it. There's no tricks. You can't throw the flashlight or something like that. You have to carry it. Make this so you can see the whole thing here. Is that going to work? There, I'll leave that up. You can see that. Take a picture of it on your phone if you want to. And you can work the rest of the period. I'll put the assignment up right now and you can work on it.